have with us today Kaitlyn Rodriguez. Kaitlyn earned a bachelor with honors in biomedical science alongside a double minor in psychology and computer science from the Toronto Metropolitan University in 2021. She is currently a Master Bioinformatics student under the supervision of Dr. Dan Tupan from the Department of Animal Bioscience at the University of Guelph, and her current work involves evaluating and validating novel detection methods based on near-infrared spectroscopy for common veterinary antibiotic residue in milk samples. Thank you for being with us today, Kaitlyn, and the floor is yours.
Thank you so much for that lovely introduction, and thank you to everyone here for coming to my talk. I am very excited to be able to share a part of my thesis project today, which involves identifying a threshold of detection for common veterinary antibiotic residues in near-infrared milk spectra. Here is an overview of my talk today, starting with a little bit of background. While antibiotic residues are rare in the milk leaving dairy farms, antibiotic testing is done at multiple stages in the dairy production process in order to ensure food safety. Regulatory agencies around the globe have established guidelines regarding the maximum level of antibiotic residue that is still deemed safe for human consumption. In Canada, these guidelines are known as maximum residue limits, or MRLs. Traditional methods for antibiotic testing in this industry include the Charm Trio test, the SNAP beta-lactam ST test, and the Delvo test. When these methods are used to test milk samples, a positive result is acquired when antibiotic residues are detected at or below MRLs. However, there is concern surrounding the instances where farmers may be heavily penalized when they are not actually in violation of MRLs due to the sensitivity of these traditional methods. Following from this, there has been academic interest in exploring alternative detection methods. In the literature, there are several studies looking at the combination of either near-infrared or mid-infrared spectroscopy with statistics-based analytic techniques in order to detect antibiotic contamination in milk. Here on the slide are just two examples of these studies where coincidentally, they're both looking at tetracycline contamination. However, there are other studies looking at some other veterinary antibiotics. And here, the study on the left, they are looking at both near-infrared and mid-infrared spectroscopy paired with statistical modeling, whereas the study on the right only looked at mid-infrared spectroscopy. Of note here, I wanted to draw your attention to the number of contaminated samples used in both studies. Here on the left, we have 60 compared to 175. And we have the antibiotic concentration range that they're interested in investigating. On the left, we have a range between 0.04 to 2 milligrams per liter. And on the right, we have 0.01 to 0.4 milligrams per liter. What is important to recognize here is that these studies were looking to investigate antibiotic contamination that is around MRL level for tetracycline. In terms of their analytic methodology, both studies were interested in looking at partial least squares. And as a summary for the results that these studies produced, the first study on the left reported R-square values of 0.85 to 0.87 for the lower range of their concentration exploration, and then 0.61 to 0.67 at the higher range of their antibiotic concentration investigation. And then this study on the right, there are R-square values that are reported to be 0.989 to 0.999. For context, a score of 1 is the highest you can have for an R-square value. So unlike what we saw in the previous slide where there were two examples of near-infrared spectroscopy paired with statistical modeling, among others that are out there, the pairing of near-infrared spectroscopy with machine learning instead of statistics-based modeling has not yet been validated in the literature. We are specifically interested in this pairing because it offers the potential for automation, and if validated, this technique could offer affordable, rapid, and systematic testing that aims to provide improved accuracy compared to traditional methods. And again, if validated, this method could be used to reduce the risk of erroneous fines for farmers and reduce the unnecessary waste of milk that is deemed safe for consumption. Before moving on, I'd like to take a pause here to give a little bit of context behind what near-infrared spectroscopy and machine learning entail. Starting with near-infrared spectroscopy, on the left-hand side of the slide here, we have a representation of the electromagnetic spectrum, where we see near-infrared light existing between the wavelengths of 780 to 2,500 nanometers. Near-infrared spectroscopy is a rapid, non-invasive, inexpensive, and non-destructive method that is commonly used for identifying constituents in a milk sample, such as proteins or protein content. And this process involves a near-infrared light source being directed at a milk sample, and we have a detector that is collecting absorbance measurements at specific wavelength intervals across the full near-infrared light range. The collection of absorbance measurements for a given sample is referred to as a spectrum. And so if we have many samples, all of those associated spectra can be compiled into a data set such as the one you see here. So each column here represents or corresponds to a wavelength interval where absorbance is being measured. And the values within the table are our absorbance measurements. Each row here, as I mentioned earlier, corresponds to each spectrum for a given milk sample. The spectra in a table like this can be visualized in a plot such as this one, where we have absorbance on the y-axis and wavelength on the x-axis. So given that the constituents of a milk sample will absorb the near-infrared light based on their chemical structures, we expect to see different spectra for pure versus contaminated milk. Moving on to machine learning, I am providing a very brief overview of what this entails, but for now, we'll describe it as an approach to data analysis that involves computer programs that automatically improve in performance when given more data, as opposed to some kind of human intervention. Here, I'd like to draw your attention to two different methodologies within machine learning, that being unsupervised learning and supervised learning. Starting off with unsupervised learning, we're interested in clustering algorithms in this part of my project. In this case, we have unlabeled data that we want clustered into different groups depending on some kind of similarity measure. Now, depending on which clustering algorithm is used, different similarity measures may be used, thus meaning that from the same starting data set, we might get different clusters produced by different algorithms. As a very simplistic example here, we have different breeds of cows, and the data here is unlabeled, and what we want here is our algorithms to divide our data into different clusters based off of some kind of similarity that the algorithms pick up in the data. For example, the algorithms may produce two different clusters here, grouped by the color of the cows, whereas another might cluster our unlabeled data based on the pattern that is picked up in the data here, or the pattern of the cows, I should say. Moving on to the supervised learning, we're interested in classification in this part of my project. In contrast to the unsupervised learning, we have labeled data here of all of these examples of different cow breeds. And so if we have many, many examples of each of these breeds, we can take our classification models and train them on this data set. Once these models have been trained on this data, we then task these models with applying a correct label to a test sample that has never been seen by the models before, such as this one here. And once the models apply labels to this new unseen data, we can evaluate their performance. So with all of that in mind, you have a little bit of context behind the methodology and the technology that we're interested in for the objective of this part of my project. which I mentioned involves identifying a threshold of detection for common veterinary antibiotics using this pairing between near-infrared spectroscopy and machine learning modeling. So to investigate this objective, we use the two different analytic approaches that I just mentioned. So we have our unsupervised clustering approach and we have our supervised classification approach. And these two approaches will be covered in sections 3 and 4 of my talk today. So here we'll start off with the unsupervised clustering approach. In this section, there will be 3 different subsections. We'll be looking at the data collection, the methods for data analysis, and the results for our clustering approach. Starting off with data collection, the data for this that is explored in this approach comes from experiments that I will refer to as our threshold of detection experiments, where we are looking to identify the concentration of antibiotic required in order for our technology to distinguish between control versus contaminated samples. First, in 0% milk, we have different concentrations of all of our antibiotics of interest. So here we have crystalline tetracycline, crystalline ampicillin, crystalline penicillin G, and suspension penicillin G, all common veterinary antibiotics. And these contaminated samples with different levels of antibiotic in them are then compared to our control samples that have no antibiotic. Then the same structure carries over to our experiment where we're looking at the same antibiotics, but now in 2% milk. An important note here is that each of these samples were heated and then measured to be 36 degrees Celsius right before we took our near-infrared spectroscopy measurement. This slide here is a representation of the concentrations we investigated for each of our antibiotics. So starting at the top, we have our crystalline tetracycline, looking at concentrations between 654 to 2,160 milligrams per liter, and then the same all the way down. To mention, there is some color coding here. At the bottom, we have a little legend. So the concentrations in blue are the concentrations we looked at in 0% milk. Concentrations in red, we looked at in 2%, and then anything in green were looked at in both 0 and 2% milk. And you'll notice that the range of investigation is different between each of our antibiotics. And this is because in some cases, such as with tetracycline, we had prior experiments that produced results that allowed us to narrow down where we think the threshold of detection would be. In contrast with crystalline penicillin G, this third one here, we did not have that same prior observation to rely on, so we had to explore a much wider range. Now, before going into explaining different methods for data analysis, I first wanted to provide an overview of what the spectra look like and how we'll be working with the data. So in this plot here, we have the spectra straight from the near-infrared spectroscopy device without any kind of pre-processing. And so what I want to bring to your attention here is that at around 1650 nanometers and beyond in our spectra, we see this very high amount of variation in the spectra that seems to be related not to variation in our samples, but rather it seems to be an artifact of the limitations of our device. And so in order to prevent any kind of influence on our analysis, we chose to trim the spectra to exclude the spectra at 1650 and beyond. And then once we had this data set of our trim spectra, we then duplicated this data set and applied an algorithm known as recursive feature elimination. This algorithm allows us to keep only the wavelength intervals within the spectra that are most informative when we're distinguishing between different levels of contamination. So now that we have these two data sets on the right-hand side here, we applied some different methods for data analysis. We employed a qualitative analysis, a principal component analysis, we used t-distributed stochastic neighbor embedding, and we employed 3 different machine learning clustering algorithms known as k-means, spectral, and hierarchical clustering. So for the sake of time here, in the next few slides, I will be showing the results for crystalline tetracycline in 2% milk. The same process that you'll see here was applied to all of our different antibiotics in both 0 and 2% milk. Starting off with our qualitative analysis, this is what the spectra look like for crystalline tetracycline in 2% milk. We have control in blue, our lowest concentration of 654 milligrams per liter in red, our second highest at 1,156 milligrams per liter, and then our highest at 2,160 milligrams per liter tetracycline. And so in order to illustrate the pattern that we've seen here, I will magnify this region of the spectra here, which also corresponds to this region here. And I'm only showing the average spectra. What that means is for each concentration, we had 3 samples. And so we took the average of the 3 samples at each concentration to get the average here. And the important observation is that we see quite a bit of overlap between the control, the lowest, and the second lowest concentrations of tetracycline. Whereas with this highest concentration, we see that there's quite a distinct difference in the amplitude of the spectra here. And so from this analysis, qualitative analysis alone, it would suggest that the concentration required to see a difference between control versus some kind of contamination lies somewhere between this concentration in the green and this one in the purple. Moving on, here are the PCA plots corresponding to our 2 data sets. Again, we have our trim spectra on the left and our spectra that were trimmed and had RFE applied. In both cases, we see this distinct separation of our highest concentration in these purple points here. So these are our 3 samples at our highest concentration. The proximity of the points on these plots indicate similarity, and so we see that the control and the lower concentrations seem to be more similar to each other, and then this highest concentration seems to be different from those or distinct from those. Moving on, we have our TS&E plots similar to PCA. We see this separation of the highest concentration away from the other points. Finally, we have our machine learning clustering algorithms listed here, k-means, spectral, and hierarchical for both our trim spectra and our spectra that were trimmed and RFE applied. Here is a representation of the different samples. We have our 3 controls and then our 3 samples at each concentration. So as I mentioned earlier on, when we're working with our clustering algorithms, the algorithms don't rely on labels to produce their clusters. Rather, they're looking at the data itself and using a similarity measure to divide up the data into clusters that are similar to each other. So here in both data sets and across all 3 algorithms, we have a cluster that contains the control and the lowest concentrations, and then we have a separate cluster of this highest concentration. So taking into account our qualitative analysis, our PCA, our TS&E, and then the clustering results we see here, we have concluded that the threshold of detection for crystalline tetracycline in 2% milk lies between these 2 concentrations. And so this same process of going through all of these 4 analytic methods is applied to all of our antibiotics of interest and in both, again, 0% and 2% milk. This slide is a summary of what we've observed. What we just spoke about was is listed here. We have our 1,156 to 2,159 milligrams per liter crystalline tetracycline in 2% milk. And then you can see what it looks like, or what we saw in the 0%, and then the same for each of these antibiotics. One thing to note is this range here is notably a lot wider than the rest. An explanation behind why that is this was our starting point, and as we continued on with our threshold of detection experiments, we decided to aim for much narrower ranges for our threshold. And so given more time, we would love to make this a little bit more narrow, but we'll have to see what the timeline of completion for this project. This may have to be left as a next step for future work. Now for our supervised classification approach. Again, we have our three subsections of data collection, data analysis, and our results. So in contrast to the last section where we had our threshold of detection experiments, now we're working with 12 different experiments based on 7 different experimental variables we are interested in investigating. And this gave us a total of 612 samples to work with instead of the 12 samples for that crystalline tetracycline example. And so in this next little bit, I will show a representation of what these 12 experiments look like. However, I won't be going into much detail on that. But just so there's some clarity, there is a legend here for the different symbols that will show up in the representation coming up. We have symbols for the different antibiotics we looked at, the different antibiotic forms, the dilution protocols that we use to obtain our concentrations of interest, the devices that we used for measurement, and then we even have a little symbol here for milk that was collected from Alora. And so going step by step, we have our first variable of interest, which involves sample temperature. We have 5 experiments represented here. We have dilution protocol, threshold of detection that came up in the last section, choice of spectrometer, fat content, milk brand, and the form of the antibiotic. And so what's important to note here is that there are some experiments like this one here that are relevant to various different topics, but overall, this is a collective of 12 unique experiments. And so through all of this experimentation, we were able to assemble this data set, as I mentioned, of 612 samples. And so when compiled into a single data set, it looks something like this, where we have 211 wavelengths at which absorbance is measured. So at the beginning, I mentioned we have columns for the different intervals where the absorbance is measured. These values in the table are the absorbance measurements themselves. And this final column here acts as our label. So we have samples labeled as being above threshold or below threshold, given a chosen threshold of 1,160 milligrams per liter in this case. This concentration was chosen as it gives us an almost 50-50 split of samples being above and below threshold. We have 52.5% of the samples being labeled as below this threshold. And as I mentioned, a total of 612 samples. Here is a histogram illustrating the number of samples corresponding to our different antibiotics of interest, and then also a representation of our controls. And so in order to analyze this data set, I worked with 8 different machine learning classification models that were trained and then tested. And then on the right-hand side here, we have a list of the 7 evaluation measures that were used to see what the performance was of these models. For our results, we have here the performance scores of the models when they were trained and then tested on an unseen data subset. And so here at first glance, it appears that our random forest model exhibited the best performance as it has the highest score across all of the evaluation measures along the side there. However, before jumping to a conclusion and, saying that our random forest is the model we want to go with moving forward, it's important for us to consider the learning curves of each of these models. Here are examples of the learning curves that I've mentioned. To break down what we're looking at here, we have our random forest model that seems to be the best performing along the top. So this is the learning curve before the model was optimized and then after the model was optimized. And then for comparison, we have a model known as logistic regression. Here is the learning curve before optimization and then the learning curve after. And so here in our random forest model, we see evidence of something we refer to as overfitting. And it is made evident when we look at this gap between the training score and the cross-validation score of this model. So in our case, cross-validation score is used to evaluate the performance of these models while they're still in the training phase. And so when we see that a model is overfitting, it means that when these models are being trained on the training subset of data, they are memorizing the training examples that they're given, as opposed to learning from their training and then drawing generalizations that could then be applied to new unseen data. And so what we see here is that these models perform very, very well on training examples because they were memorized, but then when they're applied to other data that was not shown to the model before, they won't perform as well. In contrast, with a model like logistic regression here, we do not see that same notable gap between training and the cross-validation scores. However, overall, we see that, at least for the training score, it's not doing as well because, again, it wasn't memorizing those training examples that were shown. So here we now have the 4 models that were identified as being overfitting, noted in orange, and we are not going to be considering these models moving forward. So when we draw our attention to the remaining 4 models here, we can see that the logistic regression model is the best performing now with a highest score in each of these measures here. These are 2 plots comparing our algorithms before and after they were optimized. However, as I mentioned, we're not considering the models that are overfitting. So when we focus on the remaining models, we see that overall the performance before and after optimization is about the same for most of the models, except our multi-layer perceptron, where we do see an increase in performance there. Confusion matrices, such as the ones seen on the screen here, can also be used to investigate model performance. First, I'd like to draw your attention to this quadrant here. So these samples are in reality below the threshold that we chose, and the model logistic regression assigned it a correct label of being below threshold. In this quadrant here, these samples are in reality above threshold and were also provided the label of being above. In these 2 quadrants here, we have the mislabeled samples, and so when we compare logistic regression to another model that was not overfitting, naive Bayes, just as an example, we see that in comparison, these scores in the yellow quadrants at the top, and then this quadrant here, the logistic regression has an increase in the samples that were correctly labeled, and then in these 2 quadrants, we see a decrease in the values, meaning that the logistic regression model had less misclassification, which is indicative of the fact that the logistic regression model performed better than the naive Bayes. Finally, we have 2 plots here that allows us to investigate the importance at different wavelengths within our spectra. On the left, this is a spectral plot for the full data set of 612 samples. And on the right here, these are the top 20 wavelengths that were used by this model in order to identify if a sample was above or below threshold, or I should say was used to classify above or below. And so the color coding here of these bars correspond to the region that they correspond to in this plot here. So these red bars here correspond to this region, the green bar here, the blue bars here, and then the purple. And so this gives us a way to visualize which parts of the spectra were most informative for our best performing model. So in conclusion, through our unsupervised clustering approach, we were able to identify a threshold of detection for each of our antibiotics of interest. However, since the thresholds that we identified were at concentrations much higher than the MRL levels of those antibiotics, these results suggest that our technology is not sensitive enough if we're looking at milk with no antibiotic and milk with just a little bit of it at around MRL level, which is in practicality what we'd be interested in. And then through our supervised classification approach, when classifying samples as being above or below a chosen threshold of 1,160 milligrams per liter, we saw 4 models that avoided overfitting, meaning that they generalized their training to classify novel samples. And of those 4, the logistic regression model exhibited the best overall performance with an accuracy of 74%. Now, again, if we think about this through a practical lens, we would not want to settle for a methodology that is only accurate 74% of the time. We would want to aim for implementing a technology that is, say, 99% accurate. And so what's interesting is these results here are not reproducing some of the results that we saw in prior studies, looking at the same technology for the same purpose. So if we can remember at the beginning of my talk, those 2 studies that I mentioned, they were looking at very low concentrations of antibiotic that were around MRL level, but they were also reporting very high performance, higher than what we're seeing here at a concentration that is at a much higher concentration. So when this was first happening, it was very puzzling why we could not reproduce the observations that were previously seen. So we embarked on this pretty hefty investigation of what might be going on here. And so we've acquired results since then that lead us to suspect that there's more going on, or there's more at play that were not described in the prior studies. What's unfortunate is that the experimental setup of these previous studies are not well documented, and there are certain experimental variables that we've identified as possible confounding factors that are not addressed in these previous studies. So for example, one of these variables is the sample temperature. We've found that it is important to control the temperature of the sample right before you take the measurement. In these previous studies, they do state the temperature at which the samples were stored, but did not state the temperature at which these samples were measured. And so if these previous studies were not controlling for the sample of their temperature, the temperature of their samples, it's possible that there were confounding factors that were not controlled for, and that may have affected their analysis. And so this whole investigation into possible confounding factors unexpectedly became an important and substantial part of my project. But it is a worthwhile endeavor because it is not well explored in the literature thus far, especially for considering that this technology is well explored in the literature in contrast. And so if there's any interest in some of that other work that we've done, you'll have to keep an eye out for my thesis that will hopefully be completed and available soon. Moving on from that, I'd like to take the last few moments of my talk to thank the people that have made this project possible. This includes Dr. Dan Tulpen and the Tulpen Lab, Dr. Ventura and Dr. Berriero from the Bioma Lab at the University of Sao Paulo, Dr. LeBlanc and Dr. Bays, my other committee members. I'd like to thank Food for Thought, Canada First Research Fund, Research Excellence Fund, and NSERC for their support. And I'd like to thank Kristen and Samla for the invitation today. I realized I've also forgotten to include Lauren Fletcher. I saw her in the audience today. She is the whole reason why we could have conducted all 12 of our experiments across however many months it's been. Without her, we wouldn't have this project in the way that we have it now. And finally, I'd like to thank everyone else here for your time and attention. Thank you.
Thank you, Kaitlyn, for this lovely presentation. It was absolutely amazing. Thank you for accepting our invitation. So if anyone has any questions for Kaitlyn, please, you can raise your hands, turn on your cameras and microphones, and ask her. So yes, Colin, you can go ahead.
Hey, thank you, Kaitlyn, for the for the great talk. I must admit, I know very, very little about this topic, so my question could be completely foolish, but anyway, I'll ask it anyway. So I think it was around the supervised approach. It was around slide 51, and you said within your training population that around or over 50% or 50% of the samples met the respective threshold to be deemed too much antibiotics within it, essentially. Is that representative? Because to me, I'm like, is 50% of your samples are over the recommended? Is that like representative of what you would see in the field?
I wouldn't believe so. So by my understanding, within the field, it is actually very rare for milk leaving the dairy farms to have antibiotics, especially above what is allowed through legislation. But the reason why we aim for this balanced 50-50 split for our first run of the classification modeling is that it allows us to use specific evaluation measures that rely on the data being balanced. And so when we're evaluating the performance and comparing it to this 50-50 split, we can get an idea of, oh, is this model only, labeling everything as above, and it has a 50% chance of getting it right. But our logistic regression model, for example, had a 74% accuracy, meaning that it wasn't, just taking a shot in the dark and saying all of them were above and that's good enough. So in that case, it's for those reasons, it's nice to have that balanced split, but it is possible to work with data that is unbalanced as well.
Okay, so if my thing is correct, just for this, initial, see if you can. But so then if you were to go to the next step, like how would you apply this?
Right. So
unfortunately, sorry, go on.
No, sorry, I cut you off.
No, you're good. I had finished.
Okay, if I understand what you're getting at, so let's say, well, actually, we did do a run of this where instead of a threshold of 1,160, we looked at 0.01 milligrams per liter, which is an MRL for some of the antibiotics that we're interested in. In that case, the data split was 70-30. And so in that case, there were certain evaluation sorry, I'm just gonna, oh, it's the other way. So some of these measures here rely on the 50-50 split. So if we're working with 70-30, it just means that some of these measures can't be used to evaluate performance. However, when we're looking at a concentration at 0.01 milligrams per liter, which in practice is relevant, the models weren't performing nearly as well. So it doesn't seem like this approach of the near-infrared spectroscopy and then paired with our analytical approaches is not in practice what we would hope for.
Okay, perfect. Thank you.
Thank you.
Thank you, Colin, for your question. Flavio?
Hi, Kaitlyn. Very nice presentation. Thanks for doing that. I have two questions for you. The first one is just for me to understand better. The first experiment, you tested 0% milk and 2% milk.
Yes.
Right. And I think there was kind of differences that you found between 0 and 2%, right?
In this slide?
Yes. So there was difference, right? Difference between when there's 0% milk and 2% milk on the threshold or the possible threshold. So, but then in the second experiment, if I understood correctly, you used 4% milk, right?
So in this data set here, I showed it very quickly. So in some of these experiments, we have 2% milk. Here, it's very small, but we have 0, 1, 2%, 3.25. And then, as you mentioned, we have that milk from Alora. And so we were interested in seeing, I couldn't squeeze it into this presentation, but a specific chapter of my thesis, we're interested in if temperature affects our analysis, if milk fat content affects our analysis. So we have samples of different types of milk fat. And then in future analyses, we want to add that data in as its own input column and see if this milk fat percentage has an impact.
Okay, I couldn't see that was really small. I thought
Yes,
you
I know.
just mentioned, I think you said 4% a lot of milk only. So I thought was all based on 4%. Then I will ask you why you would have just 4%. Okay, so that's one. The second one is you excluded from further observations, right? The models that overfit.
Yes.
Yeah, but my question for you is, one model could overfit, but regardless, the overfit could still predict better unseen sample. So why we simply excluded the overfit? Oh, do you know what I mean? You could have two models, one that's overfit, but and the other doesn't overfit. But the one that overfit still can have a better prediction ability of unseen.
Mm-hmm.
So I don't understand why you excluded all. Like just
Mm-hmm.
that's what you said, exclude all. But did you
Yes.
look further to see if they would also not really predict better the unseen samples?
So, by my understanding, when we have an overfitting model, in our case, it did perform better. But in models that are not overfitting, the performance is more reliable. So let's say we have a new data set and we provide it to these models. It's possible that those overfitting classification models wouldn't perform as well as we saw here. So
Yeah, but did you test that?
we have
the stability, let's say, with different subsets of unseen data, or not?
So as I mentioned with the last question, we did look at a different threshold and we ran that same procedure again. And those results are still in the process of being analyzed. So I don't have a great answer for you. I'm not sure if maybe even with this new data set, those overfitting models are still performing the best and maybe we should consider them. So
Yeah.
unfortunate, yeah, I don't have a complete answer right now. Yeah.
Okay. Thanks a lot.
Thank you.
Okay, does anyone else has questions for Kaitlyn? Kaitlyn, I was just wondering, at the end you said that your model was only able to predict 74%, like a reliability. And then of course we aim for 99%. And then you also mentioned that temperature could be one of these reasons. Did you found like any other reason that could be affecting this measurements, or maybe like methodology or even like physical factors?
So this slide is actually great for this. So these are the different variables that we considered might have an effect. So I think you just mentioned even in the experimental approach. So we looked at different ways of diluting down our antibiotics to achieve the concentrations we want. We're trying to consider if maybe, as I mentioned, the fat content might be playing a role. So this presentation is the first chapter of my thesis, and then the next two chapters is actually exploring some of these other variables that may be at play. Yeah.
Okay, perfect.
Thank you.
Oh, Kristen, yeah, go ahead. Can't hear you. We lost Kristen.
She's sitting beside me here. Her team's just. Do you want to just ask it on my computer?
Hello. I was just wondering about maybe more like the practical aspects of like implementing the technology. So normally when you, what are normally the implications of finding antibiotics in milk? Just because I don't really know the dairy industry super well.
Sure. So My understanding of the process is that on these farms, they have these bulk tanks of the milk that is collected from these cows. And those traditional methods, I'm just going to back up to the beginning. Here. So these traditional methods are some tests that can be used on the farm to check that their bulk tank milk isn't exceeding MRL levels. And then once the bulk tank milk is shipped off to a processing plant, it is tested again. So if a shipment of milk is found to be violating the maximum residue limit set out by the Government of Canada, the farmers will be penalized and the shipment will be discarded. And so the issue or the concern here with traditional methods, if these tests are too sensitive and they're flagging shipments as being contaminated beyond what's allowed, when in reality they're not, these farmers have to, they're dealing with these really heavy fines when they shouldn't be, and then that milk that is actually safe for consumption is thrown away. So the hope here is that we can come up with an approach that is more, the accuracy reflects MRLs and is not detecting super far below, or it requires like a whole bunch of antibiotic for that flag to be raised. So the goal here is to be able to detect right at MRL, and there's this whole endeavor of trying to figure out what that technology might be.
Okay, that's interesting. I was wondering too, like, is it possible to, like you did mention that it was like a rapid method, like is it possible to detect it before it goes into the bulk tank?
So this is an interesting discussion that I've had with my committee members. So I'm also not the most, how should I say, my background isn't exactly in this field. So I'm, new to it as far as I've learned through my master's degree. But by my knowledge, there are robotic milking arms that are used to milk the cows. And from what I've learned, there is some technology attached to those arms that are already doing some analyses. And so, years down the line, if this could be implemented and is found to be sufficient for this purpose, the idea is, hopefully we could find a way to implement a near-infrared light source right there on the robotic arm. So as the milk's coming out, it could be scanned right there.
Okay, interesting. Cool,
Yeah.
Thank you. Nice presentation.
Thank you.
Okay, do we have any other questions from anyone? Okay, no one? Okay, so I'd like to thank you again, Kaitlyn, for your lovely presentation. And also I would like to thank everyone that joined us today. Yeah, have a happy Thanksgiving, everyone. Nice long weekend, and we'll see you all next Friday.
Thanks, everyone.